Hello everyone. In our lecture series based on vector analysis, in the previous video we discussed derivative of a vector. We studied how to find derivative of a vector, and in that case the vector function depends on some quantity, which is often scalar quantity, time. Derivative of a vector involves the dependence of vector function on single quantity. Here a was the vector function and it was depending on this scalar variable t, which is time here. So whenever there was change in time, we were expecting the change in vector function a. This is how we study derivative of a vector. Suppose c is any vector function, c is any vector, but here let's say it is a constant vector. Now we are saying that in derivative of a vector, whenever there is change in time, we expect change in vector function. But if the vector is itself a constant vector, which means that it will not change with time, then what would happen to this quantity? Then in that case, dc by dt would be 0, simply 0, because we will not get any answer. This thing only represents that how would the vector function c change whenever there is change in time. For small change in time, whatever small change in the vector function takes place, this quantity tells us that value. But if, okay, time will definitely change, time just goes on and on, we cannot stop it, we cannot control it. So it will definitely move. But if with the change in time, c vector is not changing, then this whole quantity would be meaningless and it would give us the answer 0. So derivative of any constant vector is always 0. Then we also know that we can express any vector. Suppose c is the vector and we say now let's give it some other name. We are taking c to be a constant vector, but let's say we have another vector b which obviously depends on t. So in that case, if we have to expand it, now you know that whenever we have any vector function, we express it, we expand it in terms of its components along with the directions. So we can mention it as bx, which would be depending on t, and I cap. Okay, so this t would be included. See, otherwise whenever we write any vector function a, we don't know that on which particular quantity it depends. We simply say that okay, this is the vector and we express it as ax I cap plus ay j cap plus az k cap. But in case we know that the vector function, the vector actually depends on some quantity, in that case all its components will depend on that quantity. Now whenever we express vector with some quantity within the parentheses, that means that vector depends on that quantity. Whenever that quantity will change, there will be change in the vector. So then if the vector itself as a whole depends on quantity, then all its components would be depending on that quantity, because ultimately direction, all we have got in a vector is magnitude and direction. Direction will stay as such, but we would expect change in the magnitude with time. If something is moving forward, suppose a car is moving on a straight road, it's a straight path. So after 1 hour, 2 hour, we expect that the distance would change, but the direction would stay the same. Here you can see that suppose at time t equal to 0, whenever we start any measurements, well, time is never 0, it is a continuous quantity which is just moving forward. But whenever we make any observations, we consider time to be 0 and then we measure time from that instant. But if I am saying at t equal to 0, that means this is the initial observation. So let's say the time actually is 10 a.m. Car is here. This is distance x equals to 0. Now time is moving forward obviously, and as time goes, the x also increases, the distance also increases. So suppose now this is x equal to 0 kilometer and this is x equals to 20 kilometer, and this is the position of car at time t equals to 2 hours. Okay, let's say this is 12 noon. So now the direction is not changing. The car is moving on the straight road, but the distance is changing. This is what we mean by that here, whenever any vector quantity depends on some quantity, some other quantity, then all its components which represent the magnitude, they also depend on that quantity individually. And that's why here we will express it as, this is how it is. We will express vector in terms of its component as well as direction, but each of the component would individually depend on that scalar quantity. So that's why we say that the components of the derivative of a vector are derivative of the components for fixed directions. That means if there is vector b which is depending on t, then all of its components would depend on t, and if we have to find the derivative of b with respect to t obviously, then separately all the components, we would take the derivative of all the components with respect to t, because all the components individually depend on time. Here the variable. This is the final expression. One thing to notice in derivative of a vector is that derivative is always when the vector depends on only one quantity. Only one quantity. That means the dependence of vector is only on one quantity. Only one quantity would affect that vector, nothing else. Whenever we take derivative, it's always with respect to one vector. One quantity, one particular quantity. Here t is the quantity. So we have taken dv by dt, or we say dc by dt, because vector depends on single quantity t. Whenever time changes, the value of vector would change. And it's not always about time. We can consider some other quantities also. Not always we take derivative with respect to t. In most of the cases, derivative is with respect to t, that we often study all the vectors with change in time, because that is the most important measurement, that how something would change with time, because time is just moving on. But there could be some other quantities also. So we can take derivative with respect to those quantities also. Could be with respect to some distance, some direction, some other quantity. But the thing is, derivative is always with respect to one quantity, always one. But what if the vector function depends on more than one quantity? In that case, what we take is partial differentiation. See, with respect to t, this is a complete differentiation. We simply called it differentiation, because single variable, single quantity is involved. It's just the time and nothing else. C depends on time or B depends on time, and we are taking the derivative. So this is differentiation. But what if this vector function b depends on more than one quantities? In that case, we have to take the differentiation of b with respect to all those quantities, because whenever those quantities will change, b will change, because it is depending on that, on those quantities. So in that case, we cannot say that we are taking differentiation. Instead, we say that we are taking partial differentiation. So now we are going to introduce partial differentiation, and for that the operator, the symbol that we use is del operator. See, d simply represents differentiation and del represents partial differentiation. And often whenever we have to take the differentiation of any vector quantity with respect to different variables, if we know that that vector function depends on many quantities, then we use this symbol. If A is depending on x, y and z, then we will find curly A by curly x, curly A by curly y, curly A by curly z. So this we call it curly. See, this is the normal D and we have curled it a bit. So we call it curly. Curly A by curly X, curly A by curly Y, curly A by curly Z. So this is the case of partial differentiation. Partial means not complete, something which is not complete. So here it is not that A totally depends on X or totally depends on Y or totally depends on Z. It is not the case. Here we are saying that A depends on all these three quantities. So that's why we have to take the differentiation, because whenever we want to check that how A would change when there is change in these quantities, we have to use differentiation, but that differentiation won't be with this D. That would be partial differentiation, because A partially depends on X, partially depends on Y, partially depends on Z. So that's why this is the representation. And when we include all the quantities, like mostly all the coordinates X, Y, Z, then in combined form, we denote all these by this del. So this is our del operator. It's simply a mathematical operator just to represent. So the physical significance of partial differentiation I have told you, but this thing is totally mathematical. There is nothing hidden in it. It's just mathematical operator. If A was simply depending on X, in that case what you would have done? You would have taken differentiation. You would have said dA by dx, and that's it. Because A is depending on X only. No other quantity is there. But if A is depending on more than one quantity, then you have to take partial differentiation. So always remember, differentiation is for when dependence is on one variable, one quantity, and partial differentiation is for when dependence is on more than one quantity. This is an important observation, important rule to remember. Whenever there is dependence on single quantity only, single scalar, usually we take differentiation or partial differentiation with respect to scalars. Always we study dependence of vector quantity on scalar. It's always the dependence of vector quantity on scalar or on scalars. So when we first studied derivative of a vector, that was the dependence of vector on time only. So time is a scalar. Then if we are going to study partial differentiation and we are saying that vector A depends on x, y, z. So x, y, z are also scalar variables. Okay. So we always, most of the time, we study dependence of vector quantity on scalar. This is an important observation. And then to understand derivative of a vector, I took an example of dependence of poverty on population. We said that population is independent variable and poverty is dependent variable, which is depending on population. And we studied that as population increases, poverty increases. So there, population was the only variable on which poverty was depending. So that was the case of derivative of a vector, and we had taken differentiation. But now what if there are more factors on which poverty depends? Consider this example now again. We have poverty. But now we are studying that poverty is depending on three variables, three quantities. Those three quantities are population, illiteracy, and corruption. So now we have to study that how poverty changes when there is change in population, how poverty changes when there is illiteracy among people, and how poverty is affected when there is corruption in society. Now, whenever there will be change in any of these three parameters, poverty will be affected. So this study is all about dependence of poverty on population, illiteracy, and corruption. Now, population is independent variable, illiteracy is independent variable, corruption is independent variable. And who is dependent? Poverty, because poverty is depending on all these three variables. So whenever there will be some change in these three, poverty will be affected. We will study the influence of these three parameters on poverty. Now, if we have to mention it, then we can write that poverty, the way we represent any vector, we say that vector A depends on X, Y, Z. So that simply means that poverty depends on population, illiteracy, and corruption. So this is dependent variable, and these three are independent variables. And whether it is differentiation or partial differentiation, that is also always taken of dependent variable. Suppose here A is dependent variable, which is depending on X, Y, Z. So partial differentiation will be of A with respect to X, with respect to Y, with respect to Z. Similarly, here poverty is dependent variable. So the partial differentiation of poverty will be with respect to all these three. So partial differentiation of poverty with respect to population, partial differentiation of poverty with respect to illiteracy, partial differentiation of poverty with respect to corruption. Just to understand, because we cannot combine all these three factors as these are independent variables. So we cannot merge independent variables. They are independent. The name itself says that they will vary on their own. But poverty is dependent variable. So to study the effect of all these three on poverty, we have to take partial differentiation first. Partial differentiation allows you to deal with all the three parameters individually. That if we take partial differentiation, we will be taking poverty with respect to population. Okay, we will write that curly poverty, if it's a vector, suppose, upon curly population. This would tell us that how changes in population is affecting poverty. Similarly, partial differentiation of poverty with respect to illiteracy. So we'll say curly poverty upon curly illiteracy, and then we will take the partial differentiation of poverty with respect to corruption. So we'll write curly poverty upon curly corruption. So this would tell us how corruption affects the poverty. So we will take the partial differentiations individually, and then we will combine all these three to get the final answer. So this is how we perform partial differentiation. Let's see how to write it down mathematically. So if vector A is depending on more than one scalar variables, for example x, y, and z, then we write vector A as vector A with x, y, z in the parentheses, because it is depending on all these three. Now again we have to define it the way we defined derivative of a vector. Same way we will define partial derivative of a vector. So, but the only condition is that the limit should exist. Okay, so now if I have to write down partial derivative of A with respect to x first, then that would be curly ax by curly A of x, you can also say, is equal to limit. Now the important thing to understand here is that we are finding partial derivative of A with respect to x. So the change in x, we will observe the change in A. Now here, since A is depending on all these three scalars, we cannot just ignore any of the scalars. So if we are studying the partial differentiation, or if we are studying the dependence on one of the variable, one of the scalar, we have to mention other two as well. So this is the original state, that is depending on x, y, and z. But now we are saying that for change in x, what would be change in A? So that's why we have to write here A of x plus delta x, y and z as it is, because here y and z are not changing. We are only studying the change of x. So delta x is the limit. Limit tends to 0, that it has to be very, very small change. Whatever change we are studying, the change should be really, really small. So here it would be x plus delta x, because only x will change. Here we are considering, because we cannot study any effect by considering the changes in all the three variables simultaneously. We cannot do that. We cannot do simultaneously. That's why we study the effect of one scalar step by step. We pick one scalar, we study the change in A with respect to that, keeping the rest as it is. Then we take the another one, then we take the third one, and so on. So what would be curly A by curly Y? Now x and z, we are not touching them, we are not treating them, we are not thinking about how are they changing, we are only concerned with y here. So here obviously the change in y should be really small, so delta y tends to 0. A of, see here the thing is same because always we subtract from the original state, so this is the original condition, and now we are studying for change in y, so obviously in the denominator there will be delta y. Now x as it is, but y plus delta y, and z as it is. And what would be for z? This function as it is, and obviously we are studying with respect to z, so change in z, small change in z, and now x as it is, y as it is, but small change in z. So this is how we represent. Now we have separately found the variation in a with respect to all these three by not affecting the other two variables. Okay, we have found the change in a with respect to x, y and z separately. But what about the total change in a? Because ultimately we are concerned with how vector a is changing as a whole. So when we consider the total contribution or total change, then we have to ultimately find d of a. Now you should know that each and every symbol that we use has its own meaning. Now here d means total change. In derivative of a vector, the vector was depending on single variable. So that's why we always used to write dA by dt, because d represents the change and it was the only change happening, as a was depending on single quantity. But here a was depending on three quantities, so we had to take partial differentiation, partial derivative of a with respect to all those three scalars. So when something is partial, we don't use d. D is for complete, for total, and partial, which is not complete, that is denoted by curly d. You just curl the d. So now for total change, what we will write, that would be just the sum of all these three. All these three when combined will give us the total change. So we will write it as curly a by curly x. This way we have represented, because the total change would be the sum of all these partial changes. But now one more thing we have to take care is that both sides should be same. Whenever we write anything with equal sign in between, then all those quantities on both sides of the equal sign should be same, unit wise, dimension wise, everything. Now here you say it's only dA. Obviously we know that dA is basically all these curly a combined, but we are also having this curly x, curly y and curly z in the denominator. So these two sides are not equal. So to remove these, and these are basically what? Some lengths, some distances, some magnitude. So we have to remove it if we want to make the two sides equal. How can we remove it? Just put here dx, put here dy, put here dz. Now these are the increments in xyz variables. Now this step we have taken for two reasons. One reason is to make the both quantities on both sides of equal sign equal, identical, because we have to remove this x portion, y portion and z portion in the denominator so that these two sides look equal, because all these curly a would simply add up to give us total dA. And also this dx, dy and dz, they are the differential increments, means increase in x, y, z variable. Now when we are studying the change in vector a with respect to x, with respect to y, with respect to z, so whatever change happened in x, that is dx. Whatever change happened in y, total change. Now see, this dA is total change or total differentiation of a. So now we are just summing up everything. So whatever, we know that x was changing, we know y was changing, we know z was changing. What was the total change in x? That is dx. What was the total change in y? That is dy. What was the total change in z? That is dz. And obviously this is outside the parenthesis because this is partial differentiation of a with respect to z. Here we are more concentrating on a rather than this z. This quantity always tells you how a is changing with respect to the quantity which is in denominator. So this is the meaning. But putting this means what was the total change in the quantity with respect to which you were differentiating a. Okay, so two reasons why we have written these along with these partial derivatives. We have to deal with those dx, dy, dz that we have written. We will actually, there is one more reason because we want to modify our formula, and that's why now we will actually modify the whole expression that we have just written here. This thing would get modified because ultimately we have to introduce the del operator. Okay, so one reason was to just equate the two quantities on both sides of the equal sign. Second reason was that we have to indicate what was the total change in all those three scalar quantities on which a was depending. And third one is now that we have to introduce the del operator, and for that we have to do some mathematical shifting. And you know, whenever we solve something mathematically, we introduce something, then we just solve it mathematically. So let's see how it goes. So now we are considering that if r is the radius vector from origin, the basic vector that we always talk of in terms of 3 dimension, so then what would be its differential equivalent? So that would be simply change in x, small change in y, and small change in z. Now remember that whenever we are just talking of the change, then that is d. But whenever it is with respect to something, see now x is changing and it is changing independently. It is independent component. It represents the x direction, x axis. So it is not depending on anything. It will change on its own. So when something is not depending on anything, then we always go for d. And when there is dependence, partial dependence, then we use curly. Okay, so this is the thing. So now this equation that we have just mentioned here, let's give it a number. Let this be equation 1 and this one be equation 2. Now we have to introduce del operator, so we have to do something. Now what if I write equation 1 as, if it's written as dA is equal to, now I'm introducing I caps actually. Curly A by curly X was there. I have attached I cap. Curly A by curly Y was there, but we have attached J cap now. And curly A by curly Z was also there, but we are attaching K cap here. So now if we have attached these I, J and K cap, then, and they were not there, so there must be something by which we can remove them. So for that, because we had this dx, dy and dz here, so that would help us. We can write it here now. Remember, this is a dot product and we are writing I cap dx plus j cap dy plus k cap dz. Now say this is the dot product of two what? Two vectors. Whenever we write anything with I, j and k caps, that means it is a vector quantity. What we have done, we have modified our equation 1 in order to introduce del operator. We know that dot product of any two vectors would give us a scalar, and this equation 1 was scalar quantity. This was a scalar quantity because we didn't have any I cap, j cap or k cap here. So if we take dot product of two vectors, that would give us scalar, and now you know that in dot product I cap only interacts with I cap, j cap only interacts with j cap and k cap only interacts with k cap. So if you take the dot product, what you will get? Simply curly A by curly X dx plus curly a by curly y dy plus curly a by curly z dz, which is nothing but equation A, equation 1. This is the same equation, but we have modified it by introducing these I caps. And now what is the next step? In the next step, we are going to again modify it. Now how to write it further? We know that this portion is what? This is dr vector. From equation 2 you can see that this is simply vector dr. Now let's club this portion and here this portion. After all the partial differentiation, we are going to remove it from A. So it becomes I cap curly by curly x. See, we are not removing anything because whatever is there, it should stay there. If we just miss out writing something, then that would be a big blunder. We are just manipulating it. We are just modifying it, nothing else. Curly by curly y, k cap curly by curly z, this thing. Dot, because dot product is here, so it will stay as it is. We cannot remove it. And then what we have done, we have taken this a vector outside. It's totally fine because vector a, ultimately if you will take the differentiation again, if you open it, this dr is already there and it is having dot product with this. So again a will fit everywhere. A will fit here, a will fit everywhere with curly by curly x, with curly by curly y, with curly by curly z. It's simply we have taken it outside. It's just for representation. Okay. Actually, now this thing has a meaning, and this is our del operator. So we can write now dA as del dot dr, and then there is vector A. Since there is no sign, no dot, no cross, so that means A is simply multiplying, and yes, it will simply fit here. Now this is the del operator. So this delta is called differential operator, or we also call it del operator, and this was introduced by W.R. Hamilton, great mathematician. And in Cartesian coordinates we can mention del as, so del is nothing but I cap curly by curly x plus j cap curly by curly y plus k cap curly by curly z. Now this is an operator. It doesn't have any meaning as it is, because see, this is incomplete info. This is partial differentiation with respect to x, but of what? That is missing. Partial differentiation of y, but of what? Of what vector? That is missing here. Partial differentiation with respect to z, but of what vector? That is missing here. So whatever vector comes, this gives us the ability to simply find the change in that vector with respect to x, y, z. So that's why this is for Cartesian coordinates. This is for x, y, z axis. If anything is changing with respect to x, y or z axis, suppose a molecule is moving and it is moving in air, in space, in a room, and we have to see that how does it move with respect to x axis, how does it move with respect to y axis, and how does it move with respect to z axis, then we have to find the partial differentiation of that molecule, that vector with respect to all these three. So all the time doing the same stuff is quite tiresome. So to ease our job, this operator has been introduced. So whenever something is depending on all three these scalar x, y and z, all we need to do is just apply del operator and find the answer. So that would give us the complete answer, the complete effect of x, y and z on that particular vector. So this is operator. It's incomplete as it is. You cannot use the del is as it is because it has no meaning. It's waiting for something. See, as we have plus, it is operator. Minus has operator. As such, they have no meaning. But when you bring two numbers, then definitely it does a task. When you bring two numbers, it definitely the subtraction sign does its task. Similarly, del is also just like them. Del is also like plus, like minus, like multiply or divide. It is operator waiting for the quantity. Whenever appropriate quantity comes, which is a vector, it just solves it in one go. We need not to find partial differentiation separately all the time. See, we did 3 times. So how tiring it is, how tiresome it is to find the limits, the differentiation of a vector with respect to all three. So this is for our convenience, that all we have to do is just take the vector and apply del on it, and just in one step it will do the three tasks. This is its important and really important. This is operator, but still we denote it by vector because ultimately its nature is vector. It is a vector operator and it can apply on any quantity. It may be applied to a scalar as well as vector function of space. It will simply do its job by differentiating that particular quantity with respect to x, y, z in one step. And as it is a vector operator, it can have scalar product or vector product with other vectors. That means it can have dot product or cross product with other vector, no problem, because either to find a scalar product or vector product, we need vectors. And this is a very good vector operator. We will not call it a vector, it is vector operator. It is applied on different vectors, but still it acts like vector also. Like you can do del dot A, you can find that here this is behaving like a vector, and you can find dot product. Similarly, you can find cross product also. So it's a versatile operator, and this is all about del operator introduced by W.R. Hamilton. That's all for today. Thank you.